Okay, we're back. We're done with the open domain methods. Now we'll move on to the closed domain methods for root finding. These includes uh, the bisection method and the regular falsi method. Okay, let's first discuss what closed domain methods are. Instead of starting from an initial guess, just like in open domain methods, in closed domain methods, we use an initial interval. Okay, let's say A and B. And then within that initial interval, we have the solution na hinahanap natin, which makes the function value equal to 0. Okay. Here we use the concept of the intermediate value theorem. Okay. So just let's have a review on the intermediate value theorem from your calculus. It says that if a continuous function f has opposite signs at some x equals a and x equals b, so meaning meron kang dalawang points and points ng interval, and then either yung function value mo at a is negative and then yung function value mo at b is positive, or yung function value mo at a is positive but your function value at b is negative, then we can say that there is a solution. Okay, meaning f must be 0 somewhere on a on the interval a to b. Okay, so ano ibig sabihin yan? Ibig sabihin yan, kapag yung function value natin sa endpoints, pag multiply natin, becomes negative, ibig sabihin, may solution or may root tayo sa gitna ng interval na yun. Okay, or within that interval. So let's say we have here yung A and yung B na endpoints ng interval AB natin. You get the function values f of A and function value at B, f of B. Okay, tapos yung f of A na to, since nasa baba ng x-axis, this is negative. And then yung f of b sa taas ng x-axis, this is positive. So if I multiply these two, we get a negative product. Ang ibig sabihin lang nun, may sure tayo na may root sa gitna or within that interval. Bakit? Kasi paano ba mag-move yung curve natin from a negative value ng function papunta sa positive value? Kailangan niya mag-cross sa uh, 0, okay, or sa x-axis. Okay, meaning, if we are sure na yung function natin is continuous within that interval, meron tayong root. Okay? I-demonstrate natin yan sa examples. But we have two closed domain methods for this course. We have the bisection method and the regular falsi method. Okay. Unahin natin yung bisection method. In bisection method, from the term itself, bisection, it's getting the midpoint of the interval. Okay? And using that as a limit in the next improved interval. So, ibig sabihin, we have an interval such that yun nga ulit, yung product ng function values at the endpoints is less than 0 or negative. Then we can determine a 0 within the interval AB by means of repeated interval bisection. Okay, so let's look at this example. We have here a function or a curve, diba? And then yung initial interval natin is composed of a1 to b sub 1 rather. A sub 1 to b sub 1. Okay, as you can see, yung function value natin sa a sub 1, which is f of a sub 1, this is positive. Okay, and then yung function value natin at b sub 1 is f of b sub 1. This, on the other hand, is negative kasi nasa ibaba ng x-axis. So this is a valid initial interval kasi yung product nila is negative. Okay, meaning merong part dyan na 0, mag-0, which is ito. Ito yung hinahanap natin na solution. Okay, sabi nga rito, by means of repeated interval bisection. So this is our initial interval. Kunin natin yung midpoint, kalahati. So this one. Ito yun. Yung b sub 2. Okay, and then kunin natin yung value ng function na yun sa midpoint na yan. Okay, and based from this graph, nasa baba rin siya, so positive siya. Negative siya. Okay, negative yung function value natin at the midpoint. So anong i-retain natin? Between the two, ito ba or ito? Itong nasa taas. Okay, kasi kailangan we always maintain na yung product ng endpoints natin is negative. So, kung negative na tong isa nating endpoint, kailangan piliin natin itong positive. Okay, so matitira ngayon si A sub 1 and si B sub 2. Okay, sige. Consider natin yan as the new endpoints, A sub 1 and B sub 2. Kunin natin yung midpoint around here. So, kunin natin yung function value at the midpoint ulit, which is at A sub 2. So, ito yung f of A sub 2. Okay, yan na isa natin bagong endpoint. Okay, which is yung midpoint ng current interval. So, this one is a positive value. So, again, yung f sub A is positive, f sub B sub 2 is negative. So, anong i-retain natin? Yung A sub 1 ba o yung B sub 2? Si B sub 2. Okay? Kasi yung function value natin sa midpoint is already positive. So, kailangan natin i-multiply by a negative function value which is at B sub 2. So, ngayon, ang updated interval natin would be yung A sub 2 tsaka B sub 2. Kunin ulit natin yung midpoint. That's yung f of A sub 3. This one is also a positive. So, i-retain natin si B sub 2 pa rin kasi siya yung negative. Okay, so yung current na nating interval is A sub 3, B sub 2. Okay, until makarating siya dito kay function solution. Okay, so that's the bisection method. So, paulit-ulit ang binabisect yung interval until makarating dun sa solution. Okay, may warning lang dito na this is not applicable to tangential roots. Okay, ano yung tangential roots? Ang example niyan is yung parabola na nagtatouch sa x-axis. For example, y equals x squared dito. Okay, tangential yan. So, yung root niya, tangent. Okay, sa x-axis. Tama naman, di ba? Hindi siya magagamit kasi nga, we know from the intermediate value theorem na kailangan opposite signs. Sabihin natin ito yung dalawa nating endpoints ng initial interval. Positive yung function value dyan, positive din ito. Okay, wala kang makukuhang negative kasi nga tangent siya sa x-axis. So, hindi mo pwedeng gamitin yung bisection method. Okay? Just so you know, yung magiging process if you transform or apply this algorithm into C program, ito yung general process. Okay? So, we have an input na initial interval. Tapos, ensure na yung product ng function values at A and B is negative. We have a tolerance value. Ibig sabihin, kapag umabot na dyan yung absolute error or less than that yung absolute error natin, stop na tayo sa iteration. Okay, and then ang output dapat ng program is yung solution S. Okay, such that yung function value at that S is 0. Okay, initialization, we have x sub 1 equals A and x sub 2 equals B. Okay, so yan yung initial interval. And then, dapat isolve ng program natin yung function value at x sub 1 and function value at x sub 2. Okay, ito na yung bisection method part. So, yung first one is to bisect yung initial interval. So, ano ba yung midpoint niyan? Add mo lang sila. Diba? Add mo yung A and B, which is yung x sub 2 and x sub 1, and then divide by 2. So, this is the midpoint sa x sub 3. So, yun na yung bisection part. And then, we get the function value at this midpoint. So, f of 3 on f of x sub 3. Okay, so kung f of 3 or f of x sub 3 is equal to 0 agad, yun na agad yung solution, di ba? Pero that's a rare case. So, most likely ito na yun, yung hindi equal sa 0 agad yung function value at the x sub 3 or sa midpoint. So, kailangan mo implement ito. Yung paggawa or pagkuha ng bagong interval. Okay? Madali lang siya kasi nga, like what I have demonstrated earlier, kailangan lang natin i-retain, okay, kung alin yung dapat i-retain from the initial interval. So, i-compare mo lang yung function values. Okay? So, yung f of A, f of B, and f sub f of C. Let's say na yung third point lagi is C. Okay, so, depende sa sign nito, positive or negative, yun yung pipiliin mo. I mean, depende sa sign ng function value at the midpoint, yung pipiliin natin between A and B. Okay, so kung positive ito, positive si function value at C, pipiliin natin kung alin yung may negative sign dito. Kung negative naman, kung alin yung may positive sign between these two. Okay, yun lang ibig sabihin nito. Sige, tignan lang din natin para lang maintindihan. If yung product daw ni f sub 2, function value at 2, and yung function value at the midpoint 3 is less than 0, ibig sabihin, si point 2 yung i-retain natin from the interval. Okay? Huwag mo nang pansinin ito kasi medyo nakakalito. Basta ang kailangan mong gawin if you implement this into C code is i-retain lang na f sub 2, ay i-retain lang na x sub 2 yung x sub 2 and then yung f sub 1 papalitan natin ng x sub 3. Okay? Alisin natin yung x sub 3 ay yung x sub 1 kasi ang nagpa-negative dun sa product is si point 2 or si x sub 2. Okay, on the other hand, kapag yung product ng f sub 2 and f sub 3 is positive, ibig sabihin hindi natin i-retain si point 2. So, si point 2 ngayon, papalitan natin ng point 3, okay? And na-retain lang si point 1. Right? Sige. Huwag na rin pansinin yan. Mas maganda yung examples natin later sa table form. Mas madaling mag-gets. Okay? And then yung break-off criterion or kung kailan titigil yung loop or yung iteration is when yung absolute error natin, which is the difference between the, okay, para lang mas clear, absolute error for our case, for our uh, examples would be the absolute difference of x sub uh, previous midpoint, okay, or current midpoint. Okay, midpoint minus current midpoint. Absolute value naman yan, so kahit magkabaliktad. Okay, so that's our absolute error. Alright, and then kapag less than the tolerance value na or yung minimum natin na uh, allowable, not minimum, at least, at most, okay, at most tolerance level na error, pag mas mababa na dun, stop na natin yung iteration. Pag hindi, tutuloy niya lang yung pagkuha ng bagong uh, interval. So just to illustrate itong mga pinagsasabi ko na mas madali, we apply the bisection method into a closed domain problem. We're asked to find a solution of x squared minus 3x plus 1. Ito rin yung function kanina dun sa close, sa fixed point iteration tsaka sa Newton-Raphson method. Then we're asked to select an appropriate initial interval. If you recall, dalawa yung roots nito kasi quadratic yan. Isa 0.3 something, yung isa 2 point something. So let's say ang initial interval natin dito is 0 and 1 or 1 and 0. So let's say yung A natin is 1 and B natin is 0. Yung midpoint, so madali lang kunin yan. Midpoint lang ng A and B is 0.5. Okay? Since bisection method ito. And then ang next step lagi dito is to get the function values at each point A, B, and C. So solve natin sa f of A, f of B, f of C. How do we do that? Solve natin, substitute natin si A dito. So substitute si 1, kukuha mo 1 minus 3 plus 1, you get what? Negative 1. Substitute si 2, si B, which is 0, 0 minus 0 plus 1, you get 1. Okay, so valid yan na initial interval kasi yung product ni f of A and f of B is negative. So that's a valid initial interval. Okay, substitute din natin tong midpoint. We get 0.5 minus 3 times 0.5 plus 1. I get negative 0.25. Okay, wala pang absolute error kasi wala tayong previous na midpoint. Okay, so looking at this, ito kasi i-compare natin. Okay, automatic kasi na sila si C or yung midpoint, siya na yung isa dun sa endpoints nung next interval natin. Okay, so ang next question is alin yung i-retain, si A o si B? Okay, since negative itong function value natin at C, piliin natin yung may positive na function value para yung product is negative. So sa case na to, si B yun. Okay, so siya yung i-retain natin. So si B, 0 pa rin. Pero si A, mapapalitan na siya from 1 to 0.5 kasi siya yung midpoint ng previous run or previous natin iteration. So siya na ngayon yung isang endpoint. Okay, so yan na ngayon yung current interval natin, 0.5 to 0. Get the midpoint, so that's 0.25, and then substitute, makuha natin negative 0.25, 1, tsaka 0.3125. Okay, again, ito ng function value na to, yung automatic for the next iteration. So since positive ito, piliin natin yung negative. Okay, so sa case na to, si A yung magkakaroon ng function value na negative. So ma-retain itong si A. So 0.5 pa rin siya sa next iteration, pero si B mapapalitan na siya ng previous midpoint. So pupunta siya dyan. Okay, and then kunin ulit yung midpoint. So for this case, 0.375, and then substitute each to the function. Ito yung makukuha. Okay, again, positive ulit ito. So, piliin natin or i-retain natin yung negative. So, si A yun. Okay, so si A pa rin 0.5. Si B, yung previous midpoint. Okay, so calculate ulit yung midpoint, bagong midpoint, function values. And since negative na itong si C, pipiliin natin yung may positive na function value which is si B. Okay, again, dito sa third iteration, negative na yung function value sa midpoint. Kaya ang i-retain natin is yung may positive na function value which is si B. Okay, this one. Okay, so si B ma-retain as 0.375 while si A, siya na yung bagong, ayun siya yung previous midpoint. Alright? So, and so on and so forth. Okay? Pag ginawa mo yung process tuloy-tuloy, as you can see, after 16 iterations, nakarating na sa mababang absolute error. Okay, isa-isa natin na ulit itong absolute error. Siya yung difference ng previous tsaka ng absolute difference ng previous tsaka ng current midpoint. So, ito yun, yung 0.25 galing sa 0.5 minus 0.25. Tama. Okay. Itong 0.0625 galing siya sa 0.4375 minus 0.375. Okay. So, itong 0.01 galing siya sa difference itong dalawa. Okay, let's say yan yung tolerance value na sinet natin. Hinto na tayo sa 16 iteration. And as you can see, paliit naman na ng paliit itong difference between the midpoints. So, it's converging na to a certain value. And sa case na to, sa smaller root ng quadratic equation na to, nagko-converge yung interval. Which makes sense kasi nasa gitna naman talaga siya niyan. Okay? Same lang naman yung gagawin mo. If we try another interval, if you recall, nasa 2 point something. So, let's try 2 and 3. Okay, substitute natin yung 2 and 3. Makukuha natin 2.5. Sorry. Kunin pala muna natin midpoint ng 2 and 3. We get 2.5. Okay. And then, substitute natin each value A, B, and C dito kay X. We get the following. Negative 1 kay f of A, 1 kay f of B, negative 0.25 kay f of C. And as you can see, negative 2 and positive. So, ibig sabihin, valid ito na gawing initial interval. May root sa gitna ng 2 and 3. Okay? And then yung function value natin sa midpoint is negative. So, i-retain natin dito is yung positive value which is si B. Okay, so si B dito from 3, 3 pa rin. Pero yung previously 2 na value, papalitan natin na midpoint which is yung 2.5. Okay, so tas ito naman ngayon yung kukuha na natin ng midpoint, 2.75 siya. Then function values, solve, and then compare yung signs. And then solve yung absolute error, difference between previous and current midpoints. And ulit-ulit lang siya, iterate mo lang hanggang yung absolute error natin is less than the tolerance limit, which is set here as 0.00001. Okay, rounded off lang to, pero less than na yan. Okay. So, 16th iteration din, nakarating siya sa root na 2.618. Okay. So, tama naman kasi that's between 2 and 3. Right? Nakuha natin yung larger root ng quadratic equation. So that's all for the uh, bisection method. Punta naman tayo sa last method natin or yung other method natin for closed domain method. That would be the regular falsi method. Okay, other term for this is the method of false position. So kung sa bisection method, ang ginagawa natin is kinukuha natin yung midpoint between the interval. Dito naman, ang nangyayari is we connect the function values or uh, yeah, the points kung saan nandun yung interval. So ito yung point A sub 0, ito naman yung x equals b sub 0. Connect that. Tapos kung saan ma-meet or ma-intersect yung x-axis, yun na yung next na i-consider as an endpoint. Unlike kanina na midpoint dito, siya yung x-intercept of the line connecting the two intervals. Okay? So, paano sinasolve, sir? Yung C na yan, gamitan lang natin ng concept ng two-point equation of a line. Okay, so let's say yung point na to is si f a and then f of a. Okay, and then itong point na to si b f of b. Okay, so yung dalawa, kukunin natin ang equation of the line using the two-point equation. Okay, kung naalala mo, that's ang two-point equation of a line, ang form niya is y minus y sub 1 is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1 times the quantity of x minus x sub 1. Okay, gawin lang natin yan dito. Sabihin natin this is point 1 and this is point 2. Okay, so y minus y sub 1, so that's y minus f sub a, f of a. Tama? Is equal to the slope, which is y sub 2 minus y sub 1, so that's f of b minus f of a. Tapos, x sub 2 minus x sub 1, so that's b minus a. There's the quantity of x minus x sub 1, so that's x minus a. Okay, tapos anong gusto natin makuha? Ito, di ba? Ano ba to? Siya yung solution or yung root ng equation nito. Ano ibig sabihin ng root? Yung function value natin is 0. Ibig sabihin yung y dito is 0. Okay, so alisin lang natin yung y na yan. So yan, isa-solve natin. Solve for a, solve for x. So basically, i-isolate yung x na ito. Okay? So pwedeng gawin is i-cross multiply itong b minus a at saka yung negative f of a dito sa taas. So meron tayong b minus a times negative of f of a. Over ito. Hindi. Pwedeng ito naman f of b minus f of a. Kasi ang gusto pala natin i-isolate is x. Sorry. Okay. So, sa kabilang side, x minus a na lang natira. So, pwede natin ilipat yung negative a, magiging plus a dito. So, a plus b minus a times negative f of a equals x. So, yan na yung x natin. And then, simplify lang natin to into one fraction. Makukuha mo is this expression. Okay? Again, yung x na yan is si c sub 0. So, palitan ko lang dito yung x ng c sub 0. Ito yung simplification niya. So, c sub 0 ang equation niya. To get, ang tawag dito is yung regular falsi point. Okay? Ang equation niya is a times f of b minus b times f of a over f of b minus f of a. Madali lang siya kabisaguhin, di ba? Yung first interval at first endpoint multiplied to the function value at the other point minus the second endpoint multiplied to the function value at the first endpoint. Tapos sa baba, wala na yung mga ito. Okay, so f of b minus f of a na lang. So that's easy to retain sa ulo natin. Okay, so kapag yung f of, pag na-solve natin tong c naught na to o yung regular Parsi point natin, substitute sa function, if na-substitute natin siya sa function and nakuha natin is 0, tapos na, yan na yung solution agad. Yan na yung S. Pero that's not the case. That's not, most likely not the case. So, kailangan natin pumili ulit. Same process lang sa ginawa natin sa bisection method. Kung ano yung magpapa-negative sa product ng function value at C, yun yung i-retain natin. Whether that be yung A sub 0 o yung B sub 0. Okay, so let's just see itong example. Ang kinompare niya is C f of A. So yung product daw ni f of A and f sub C is less than 0. So ang ni-retain niya, C A sub 0. Okay? So sa next iteration, si A sub 1, A sub 0 pa rin. And then si B sub 1, siya na si midpoint. Sorry, hindi pa ito midpoint. Yung regular falsi point. Okay? On the other hand, kapag greater than 0 naman yung product ni function value at A and yung function value at the regular falsi point, syempre, ang ma-retain is si B. Okay, so si B sub 1, B sub 0 pa rin. And then yung A natin dun sa next iteration is C na. So like regular falsi point. Okay, let's just look at this demonstration. Okay, ito yung dalawa nating endpoint. And then, ito yung intersection. So, yan na yung next function value natin. And ito ulit. Intersection. Okay. Ulit. Pero basically, same lang talaga yung process niya with the bisection method. Okay, again, ito yung initial points natin. Connect natin, intersection, okay, and then kunin yung function value. Okay, since positive yan, i-retain natin itong negative dito. So, sila naman i-connect, intersection, function value, negative. Since negative yan, i-retain natin itong positive. And then connect, intersection, function value. Okay, since positive yan, i-retain natin itong negative dito sa baba. Connect ulit, and then intersection, and so on and so forth, hanggang lumapit siya sa solution S natin. Okay? Again, the formula that we have to use is A times f of B minus B times f of A over f of B minus f of A. Okay, so just like the bisection method, this is not applicable to get the tangential roots. Okay, so kung tangent yung function natin sa x-axis, you cannot use this as well. Right? Let's now apply this to an example. Same example lang. We're asked to find the, what do you call this? The roots or the solution to the quadratic equation x squared minus 3x plus 1. Just like what we did sa bisection method, our initial interval dito sa una is 1 and 0. Substitute. To solve for f of A and f of B, we get negative 1 and positive 1. Alright? So for this case, solve natin si C. How do we solve C? Yung formula nga. Yung C natin is equal to A times f of B minus B times f of A over f of B minus f of A. Okay, so using the values here on the table, yung C natin dito, saan siya nanggaling? Sa product nito. We get the product of these 1 and 1 minus product nito, 0 and negative 1. So we get 1 minus 0, so 1 over f of B minus f of B. So 1 minus negative 1, so that's 2. So 1 over 2, 1 half or 0.5. Tama naman itong point na to. That's the regular falsi point sa first iteration natin. Okay, and then we solve for the function value at that regular falsi point, meaning substitute yung 0.5 dito, we get negative 0.25. Okay, as you can see, valid itong dalawang to kasi ang product nga ng function values natin dito is negative. Okay, and now, yung function value natin sa regular falsi point is negative. So, anong i-retain natin? Is it A or B? It should be B kasi ito yung positive. Kasi if I multiply positive to this negative function value at our regular falsi point, magiging makakahanap pa rin tayo ng solution between these interval. So, i-retain natin si B as 0, pero yung A natin from 1 magiging yung regular falsi point na ito. Okay? And then, alam naman natin na ito, known naman na yan, diba? This one and this one. Since alam na natin itong 4 points na to, we solve for the regular falsi point ulit, yung a times b sub f of b minus b times f of a over f of b minus f of a, makukuha mo dapat 0.4. Okay, and then substitute 0.4 dito sa equation natin, sa function natin, you should get negative 0.4. Again, since negative ito, ang i-retain natin between these two is ito, positive. So si 0, 0 pa rin. Pero si 0.5 becomes 0.4 na yung regular falsi point natin na to. Alright? So, and then just repeat the process. Get the function value, get the regular falsi point using the formula, and then use the for this regular falsi point here sa function, and then you get the function value. And then compare yung mga signs ng f of a, f of b, and f of c para malaman ano i-retain. Okay, and then we look at this absolute errors, just like the midpoint or the bisection method. This is the difference between the current and the previous regular falsi point. So itong 0.1 na to, absolute difference lang nito. Itong 0.0005 na to, absolute difference naman itong dalawa. Okay, as you can see, pagdating ng 7th iteration, ang bilis, di ba? Comparing sa bisection method na 16 iterations pa, dito 7 lang, maliit na agad yung yung absolute error, di ba? So, pwede na mag-stop after 7 iterations pa lang. So, mas mabilis yung pag-converge dito sa regular falsi method sa problem na ito. Right? Okay, and then yung final na regular falsi point na nasolve natin, yung magiging approximate solution. Right? Let's move to the other interval, yung between 2 and 3. Again, function values, negative and positive, so this is a valid interval. Solve for the regular falsi point using our formula a times f of b minus b times f of a over f of b minus f of a. And then substitute that here. You should get the function value of c. Again, compare. Negative yan, so i-retain ko itong positive dito. So si b na 3, 3 pa rin. Pero yung previous nating a, instead na 2, naging 2.5. Yung regular falsi point natin sa previous iteration. Okay, and then repeat the process. You get the absolute errors until you get or you have a lower than the tolerance value. Just like the previous interval, dito sa interval na between 2 and 3, 7 iterations lang din yung kailangan. Sorry, 8 iterations rather. Okay, so yung final value ng regular falsi point yung magiging estimate natin for the larger root, which is yung 2.61803. Right, so that concludes the closed domain methods. And to summarize yung mga root finding methods natin, we have here the first three na closed domain. So fixed point, what we have to do is to derive a function g of x, tapos we just keep on substituting the values of our guesses or improved guesses hanggang makarating dun sa approximate or closest solution. Newton-Raphson, what we have to do naman kailangan is to find the derivative of the function. Okay, and then substitute yung initial guess natin. And so on and so forth. And yung secant naman, just like the Newton-Raphson, gumagamit din ng first derivative. Pero dito, hindi mo na kailangan kunin yung derivative ng function kasi ginamit niya na is yung difference quotient na concept instead of finding the derivative ng function na sometimes mahirap gawin. Okay? So, ang difference ng secant sa Newton-Raphson is you have to have two initial points or two initial guesses. Okay? Ito naman yung closed domain methods. We have bisection method and regular falsi method. So, initial guess naman dito is an interval. Okay, and then we use or apply the absolute, intermediate value theorem para makuha or mag-set ng next intervals. Okay, pero yung next interval na yun, yung isang point is always this, yung mga c, which have various formulas. Sa bisection method, yung midpoint lang ng interval, pero sa regular falsi method, ito yung x-intercept ng line connecting the endpoints. Okay, so that's all for our root finding methods. I hope you learned something, something new, something fun, and hope na ma-apply nyo ito dun sa MX natin that we'll be solving engineering problem. If you have questions or concerns about this module, you can arrange a Zoom meeting consultation with me. If you're not sure about that, you can just send me an email or post in our course discussion forums in Uflet. Again, these are our references for the mathematical module. And that's it. Thank you for listening. This is the end of the module 2. Okay, so thank you for listening.